We are finishing off chapter 4 with an application section, Markov chains. So Markov chains, huge topic. You can take entire courses just on Markov chains. Matter of fact, I just Googled, and here's one from last spring at Stanford, modern Markov chains. It's in the statistics department, actually, which gives you a little bit of an idea what kinds of applications we're looking at. Although Markov chains are very broad and are used in a lot of areas. But let's just start off with an example, since this is an application section. So I just made this one up. Suppose that out of the students that are tired today, tomorrow 70% of those will be tired and 30% of them will get enough sleep and be well rested the next day. And out of the students that are well rested today, tomorrow 55% of them will be tired, will not have gotten enough sleep. 45% of them will continue to be well rested the next day. So this is kind of the setup of Markov chains, is they have this transition from one day or one state to the next, and they assume that the transitions work the same every time. That tired people always split up a certain way, like tomorrow 70% of them are still tired. Most situations, that's a simplified assumption, which often still has some very predictive power. And sometimes it's not a simplified assumption. Sometimes situations work exactly that way. But this is one model, and all models have some assumptions built into them, some simplification. But let's just start off by doing some back-of-the-napkin computations and then see if we can get a little more efficient using matrices. So apparently today, 12 people in the class are tired, and the other 20 are well rested. And the question is just what happens tomorrow? So let's see, out of those 12 people, 12 tired people, 70% of tired people stay tired the next day. So there's going to be some tired people, and 30% of them will become well rested the next day. So we can crunch those in a minute, but let's just say out of the 20 well rested people, out of those 20, 55% tomorrow will also be tired, join the ranks of the tired, and the other 45% of them stay well rested. I think you can already see, just by me trying to do some by hand scratch computations, it's starting to kind of look like a matrix multiplication somehow already. We'll see if we can formalize in a minute, but let me just grab a calculator here and let's just crunch out these numbers. Let's see, we've got 12 times 0.70, so that's 8.4. And if we were talking real people, we'd round to the whole number to 8. But as a model, let's keep decimals so we don't lose accuracy. Let's see, where were we? So 20 times 0.55. So there's another 11 people that are also tired. And the well-rested, you could probably just subtract, but let's go ahead and do the multiplications. So 12 times 0.3 is 3.6. And maybe I will just do the subtraction here. There's 11 of these 20 that were tired, so 9 of them are well rested. Okay, so today, 12 people in the class were tired, 20 were well rested. Tomorrow, what happens tomorrow is that 19.4 are tired, and 12.6 are well rested. So there's more tired people tomorrow than there were today. And I could ask the same question again. I could just say, okay, that was tomorrow. How about the next day? And you would want to essentially repeat the same calculations with different starting numbers here. So you'd say the tired people, 19.4 tired people, 70% of them stay tired, and of the well-rested people, 55% of them become tired. So I could work out the total number of tired people the next day, and I could do the same thing over here to figure out how many people are well rested. And I will put the video on pause for a second and crunch those numbers. Okay, I just did some calculator work. And on the next day, there will be 20.51 people that are in the tired category, and 11.49 people that are in the well-rested category. The numbers are still changing. They didn't jump quite as much as they did the time before. And we could, of course, keep asking this question, how about the next day? And how about the day after that? And how about the day after that? And one of our questions will become, does this sort of settle down to a steady balance of tired and well-rested people? Or does it just kind of bounce around? And I think you can already see the amount of change is lessening. So it might settle down to a steady state. But before we try to answer that, let's see if we can get a little more efficient with doing these computations in the form of a matrix instead of just a bunch of individual individual multiplications on a calculator, because really that's all that matrices are, is a slightly more efficient way to do your arithmetic. There probably are a couple ways you could set this up with a matrix, but I'll give you a little hint as to the way we want to do it. We want to have a starting vector that describes where things are at right now. So that would be something like 12 and 20. To say today there's 12 tired people and 20 well-rested people. And we want to multiply that by something so that tomorrow, so that the result is 19.4 and 12.6. It tells us where things are at the next day. So notice what needed to happen. The 12 needed to get multiplied by 0.7. And the 20 needed to get multiplied by 0.55. Those two things together produce the new top entry of 19.4. And the 12 also needed to get multiplied by 0.30. And the 20 needed to get multiplied by 0.45. That was the 3.6 and the 9 that when we added them together, which is what matrix multiplication does, gave us the 12.6. So it looks like multiplying by this 2 by 2 matrix calculates the percentages that we want and add them together in the way that we want for the new totals. So let's just double check that to make sure that it does what we want, and maybe run through it a couple times.